So, welcome to another session of uh, GATE class on the topic of vibrations. So, quickly, I'll show you the last session, the outline, or maybe the overview. So, in the last session, we have talked about the simple definitions of what is vibration, what is a period, what is a cycle, what is a frequency, what is a resonance, and what are the different types of vibrations, starting with free vibration, forced vibration, damped vibration, undamped vibration based on the motion, longitudinal vibration, transverse vibration, torsional vibration, and this is also considered based on the applied force. And apart from that, we have discussed what is the single degrees of freedom. If you have independent coordinates only one, then this is considered as a single degree of freedom. And if you have independent coordinates more than one, then it is considered as a 2 DOF. If you have a multiple, then it can be considered as a multiple DOF. What is a free response and forced response we have talked about? If you are applying any external force, then it is considered under the category of forced response. And if you are not applying any external force, the component itself responding for the activity, then it is considered as a free response. So here the response means the vibrating nature or the characteristic of vibration. And we have discussed the relating forces to displacements, velocities, and acceleration. And we split this equation into subcategories. So this explains about the displacement. This term explains the velocity. This term explains the acceleration. And this is the externally applied force. And we talked about by breaking it into a displacement, velocities, and acceleration expressions individually. And we related to the displacement first, and then we explained the F is equal to stiffness into the displacement. That will be the condition when the system is under static condition. We won't talk about velocities and acceleration because the system is at equilibrium and as well as static condition. Next one is a damper. Damping is a viscous damper or maybe dash or part we can represent with this particular symbol, and the expression we can state F is equal to C multiplied with the change in the velocity, initial and final. What is the change? What is the difference? And multiplied with the C value. What is the C? C is a viscous damping coefficient. And FD is damping force that resists an increase in the relative velocity. And at the same time, we relate this force to the acceleration, that is F is equal to m into x double dot. We have stated F is proportional to the acceleration. F is equal to mass into acceleration. So this is again comes under the category of Newton's laws. Note that springs and dampers possesses no mass unless otherwise stated. Masses are assumed to behave like a rigid bodies. Okay, so these are the noting points, but these may not be necessary for the GATE exam. But understanding of the concept and deriving the equations, and those equations turned out to be a formula for examination, these kind of notes are important. And then we have stated how we can connect in a parallel and series of springs and how to calculate the equivalent stiffness of the system, and then differential equations of the motion for first order and second order we have drawn on the basis of free body diagram, and then we have represented Fs is equal to Kx, Fd is equal to C into x dot into T. And what is the equation we can derive based on the equilibrium condition, saying that left hand, all the forces acting left hand side is equal to the forces acting on the right hand side. If you apply the equilibrium condition, then you will arrive this equation. And the second order system, if you see spring, a damper, mass system, and if you look at spring, damping, and mass, this is a full-fledged equation, you can say, because we have all three independent characteristics of the vibration equation or the motion equation: spring, damping, as well as the mass. So you have to consider the mass along with the stiffness force, damping force, as well as the applied force. Then you take this whole free body diagram in terms of equilibrium condition, then summate all the left hand forces, summate all the right hand forces, and equalize it to m into a double dot. So then you will get the entire full-fledged equation. So this is an equation which can be considered as a full-fledged equation, which includes the acceleration, velocity, and the displacement for the applied forces, which having the coefficients of mass, damping, as well as the stiffness of the system. Then we have derived from the second order system this omega square is equal to k by m. So that means angular velocity is equal to the root of k by m. And what is the phi? Also we have represented the phase angle, and then we represented what is the c value and what is the phi phase angle with the independent characteristics as well as the independent parameters. And then we have stated what is the time period 2 pi by omega, and what is the natural frequency Fn is equal to Wn by 2 pi. In other terms, we can say that it is the inversely proportional to the time period. So that means Fn is equal to 1 by T. And free vibrations of damped second order system, we have used the non-dimensional parameters, and then we derived the damping factor is equal to C by 2 m omega n. C is the damping coefficient, and 2 multiplied with the mass of the system and the angular velocity of the system. And we have stated different scenarios. If epsilon is equal to 0, what is the condition? If it is in between 0 to 1, it is comes under the complex conjugate under damped case. If the damping viscous damping factor is equal to 1, then it is a critical damping. If the viscous damping factor is greater than 1, then it is a over damped case. So these are the cases you have to remember. If damping factor is 1, then it is a critical damping. Greater than 1, over damping. In between 0 to 1, it is under damped. And if it is 0, undamped case, the motion is pure oscillation. So these are the conditions we have to remember. And these are some of the expressions we have derived. And now we will quickly write down some of the important formulas, and thereby we will start solving some of the important problems. So that is the important step, rather going for a theoretical based knowledge, solving the practical problems or practical examples will give a better understanding of what these concepts actually represents. So without delay, we will quickly write some of the important formulas. And I'll start with a free longitudinal vibration. So this is a quick review of what we have learned. Free longitudinal vibration. We have to remember the important observations as natural circular frequency, will be represented with the symbol omega n, and which is k by m, root k by m. What is k here? K is the stiffness of the spring. And what is m? M is the mass of the system. And what is x? X is the displacement. We will explain that x. And you may not see this x in this particular equation, but it will come in the natural representation of the equation mx double dot plus sx is equal to 0. That means the kx is equal to 0. So this is the equation. So x represents the displacement here, and Fn can be written as 1 by 2 pi into root of k by m. So this is the natural linear frequency. And in the next case, if you take damped longitudinal vibration, so with the damping, you can express the equilibrium condition as mx double dot plus cx dot plus kx is equal to 0. So this is the full-fledged equation. And we have seen what is the damping factor also. C by Cc. What is this? Actual damping coefficient divided by critical damping coefficient. We can write this as C by 2m whole square, that is actually C, and with K by M. That is a CC, critical damping coefficient. And if you simplify that, it is nothing but C by 2 root of K into M. K is the mass, so K is the stiffness, M is the mass, and C is the actual damping coefficient. So that will be given if they are asking you to solve some of the problems. And here from this, we can say that Cc is equal to 2 into root of Sm, or maybe Km. So sometimes I write stiffness as a S. Along with that, we have already seen if is equal to 1, sorry, one, then it is a critical damping. Is greater than 1, then it is a over damping. Is less than 1, then the system is under damped. Right? And there is another concept called logarithmic decrement. For that, we can give the logarithmic decrement, that is delta is equal to 2 pi this damping factor is equal to 2 pi multiplied with the damping factor divided by root of 1 minus damping factor whole square. Then I will write the equations. Maybe that this one I'll consider as a 1, and this is the second one. Forced vibration So in the forced vibration, step input force and harmonic force. So we will see harmonic force based equation mx double dot plus sx is equal to f naught sine omega t. So this is representing the harmonic force. So this is not a normal force. This is a whole. As a whole, we represent this as a harmonic force. Okay. So this, how to find out the displacement? Capital X sine omega nt plus phi plus f naught s by 1 minus omega by omega n whole square into sine omega t. So with this formula, you can solve the forced vibration problem. And the next question is forced damped vibrations. So damped free response. So the equation will be something like this: plus Cx dot plus Kx is equal to F naught. This is nothing but K only. Don't get confused. F naught again. So this is a harmonic force again. So there are two conditions for this force damped equation: damped free response and steady state response. So you can give the damped free response x value will be x into e power minus damping factor multiplied with the angular velocity and multiplied with the time, and the sine of angular velocity into t plus phi. And for the steady state, we can give this as x into e power minus damping factor multiplied with the angular velocity multiplied with the time, and then sine of omega t multiplied with the t and phi 1. So this whole term actually damped free response only. I'm writing it again because it is a steady state response is nothing but a addition of damping free response, and the some other terms will add up for the next term. So this is damped free response only. Response. And then, so for the same expression, you add up another term called F naught is the applied force, and omega t minus phi divided by S minus m omega square. So that means plus c omega whole square. So this is representing the steady state response. Okay. And again, whole term is nothing but the steady state response only. But exclusively, if you want to represent steady state response term, then you can represent this term. And Another formula you have to remember that is also important is a magnification factor. What is a magnification factor? It is generally the ratio of amplitude of steady state response to the static deflection under the action of force is generally known as a magnification factor. And the expression for the magnification factor can be given as 1 by root of 1 minus omega by omega n whole square, and then again whole square, plus 2 damping factor multiplied with a omega n whole square. And now we will see another formula as a transmittivity, trans uh, transmissibility. That is represented with this kind of epsilon value, and 1 plus 2 epsilon omega by omega n whole square divided by, you can say, the denominator term, or maybe mf, or maybe you can say that it is multiplied with again mf. What is mf? This is the whole term comes here again, right? And at the resonance we can say that omega is equal to omega n. Omega n is the applied, this is based on the natural frequency omega, and this is based on the applied force. So if both are in under equilibrium, or maybe both are equal, then it is called as under resonance, at resonance. Okay, so if there is no damping in this particular equation, assume that this value is 0, then the whole term will be 1 by plus or minus 1 plus, sorry, 1 minus, actually 1 minus omega by omega n whole square. Okay, so this is the important observations you can make out: magnification factor and the transmissibility, which are comes into the category of force damped vibration. And then move on to the transverse vibration. Omega n is equal to z by delta. Delta is the static deflection. Then whirling of the shaft, how we can measure? Y is equal to E by omega n by omega whole square minus 1. At resonance, we can say that both are same. Then omega c is equal to omega n is equal to root of k by m and root of g by delta. So you can say that, so these are similar only. So this is a translatory vibration, and this is a transverse vibration, and you can correlate some of the formulas. And another important one is a Dunker-Lewis method. How we can use this method to find out the frequency of the transfer vibration of the system is equal to 0.4985 divided by root of epsilon 1, epsilon 2, and so on, and the shaft divided by 1.27. So these are all in Hertz. If the mass of the system is negligible, then epsilon shaft is equal to 0. Then the formula goes something like this. Fn is equal to 0.4985 divided by the summation of deltas. Then the next category is the torsional vibration. So the torsional stiffness can be represented with Q, G, J divided by L is the torsional stiffness. G is the rigidity modulus, and this is a polar moment of inertia, and this is the length of the system, and theta is the angular displacement of the disk that will be measured in the next equation. And how we can measure the Fn value? Fn value can be measured 1 by 2 pi root of Q by I plus I 1 by 3. In general, this torsional equation can be measured I double dot theta plus Q theta is equal to 0. If assume that there is no damping in the system. What is the G? G is the modulus of rigidity of the shaft, and J is the polar moment of inertia of the shaft of the cross section. And what is the I1 in this particular formula? Moment of inertia of the shaft. And the next important concept of the torsional vibration is a free torsional vibration and free torsional vibration with a 2-rotor system and 3-rotor system. So that is also important. We'll just make some notes and then we'll directly jump into some of the example problems. So free torsional vibration for a 2-rotor system. So in the last slide, we can mention another 2 formulas also. So that is nothing but for the torsional vibration, omega n is equal to Q by I, and Fn is equal to 2 pi by. It is similar to the translation vibration. Here we use K value stiffness. Now here we are using torsional stiffness. I is nothing but there it was mass, now it is uh, the moment. That is the moment of inertia. and then we'll move on to the free torsional vibration for two rotor system. LA, and I'll just write down, I'll draw some diagram there, but you will understand what is actually it is. And this is the central of the two rotors. I'm just talking about the two rotor system, and assume this is something big, and this is having moment of inertia A, and this is B, and this is B actually. And if you assume this is the point where you have to divide, this is the length LA and this is the length LB, and you can measure in this form. Okay, so LA and LB are the lengths of two portions of the shaft. IA and IB are the moment of inertia of rotors at A and B positions. QA and QB are the torsional stiffness of the particular length, and FNA and FNB are the natural frequencies of the torsional vibrations for a particular rotor. And how we can measure these LA and LB relations. So this can be written in this form: IB versus IA. What does that mean? Length is inversely proportional to the moment of inertia of the rotors, or in other words, LA IA is equal to LB IB, right? So for the three rotor system, free torsional vibration, for three rotor system, can be written with a final equation. I'll write IA LAIA, sorry, is equal to 1 by IB 1 by L1 minus LA plus 1 by L2 minus LC. And torsionally equivalent shaft assume that there is a shaft so the lengths are given L1, L2, L3 and L4, D1, D2, D3 and D4. So then how you will find out the total length, equivalent length L1 into D by Di, D by D1, sorry, D by D1 whole power 4 plus L2 into D by D2 whole power 4 plus L3 into D by D3 whole power 4, and this goes up to how many shafts are there. It is not only for 4 shafts, it can be generalized for n number of shafts. So if they asked you to find out the equivalent torsionally equivalent shaft length, and then you can use these parameters, all EL values of individual shafts, individual diameters of the shafts, as well as the mean diameter of the shaft. So that is how you make the design of a system for any kind of a vibration system based on these equations. Now we will quickly see how we can solve some of the examples. And here is a sum of the solved problems. A critical damping is the smallest amount of damping for which no oscillation occurs in free vibration. So the concept has been explained here. Critically damped system never execute a cycle. It approaches equilibrium with exponentially decaying displacement because the system returns to the equilibrium in fastest time, so without any oscillations. And in critically damped free vibrations, the damp force is just sufficient to dissipate the energy within one cycle of the motion. So the value of the damping factor will be given as a 1. And what are some real life examples you can give as a critically damped system never execute a cycle? Okay, so the smallest amount of damping for which no oscillation occurs in free vibration is called as a critical damping. And there is a numerical problem we can solve, and it is already solved. We can see and understand how it has been calculated or determined. So emission 250 kg mass is supported on springs. The total stiffness
So this is how we use the vibrations of the system. So with this note, I will stop the presentation, and then so as a concluding note, we can say that so the vibration for any kind of a system is to control or make the total system in an equilibrium condition to avoid such a large amplifications or large deformations happens when the total system is under vibration. So there are various vibrations and the types of vibrations also we have discussed, and the terminology which are involved in the vibration, starting from period, cycle, frequency, resonance, and to the types of frequencies such as free vibration, forced vibration, damping vibrations, undamped vibrations, and longitudinal vibrations. And what are the transfer vibrations? And what are the torsional vibrations? And along with that, what is the essence of free longitudinal vibrations and damped longitudinal vibrations, along with the equations such as damping factor and finding the natural frequency of the system. And along with that, we have covered the forced vibration using harmonic force introduced in the system. And apart from that, we have seen the damped free response and the steady state response of the system. And we have derived some of the expressions for a magnification factor and the transmissibility. And then we have derived for some of the conditions of damping factor, what will happen if damping factor is greater than 1, if the damping factor is less than 1, and if the damping factor is in between 0 to 1, what are the different kind of conditions. And it is something like if the damping factor is 1, then it is under a critical damping. If the damping factor is greater than 1, then it is over damped. Less than 1, it is under damped. And then we have discussed the transfer vibrations. So what are the different type of transfer vibrations, and what is the frequency when the resonance happens, then what is the equation for that. And we have seen the uh, Dukerley's method also in the equation, and how to find out the natural frequency using Dunkerley's method. Okay, and then torsional vibrations, starting with the torsional stiffness finding, and then with the frequency using the parameters such as modulus of rigidity and the polar moment of inertia. And we have derived the Fn values. And apart from that, we have seen free torsional vibrations, two rotor system and three rotor system. What is the equation for representing the two rotor system and three rotor system? And at the end, we have seen how to find out the equivalent length of a torsionally equivalent shaft is given for a n number of shafts are attached in a series case. So to find out L value, we have derived the expression for that. So with this, I will stop the session. Thank you.